Welcome to the module Understanding Advanced Contacts. In this module, you will analyze a closing and latching operation of the latching mechanism. Along with that, you will get familiar with the definition of solid bodies contact, as well as their limitations and uses in SolidWorks Motion. To better understand this, you will create solid bodies contact and resolve the solver errors. You will also learn how to determine the closing force required to close the latch. In Part 2 of this module, you will analyze some causes of an incorrect solution or a contact solution failure and use alternative numerical integrators. This module is divided into several topics. Click the topic titles in the list for a brief overview of each topic. The results of a motion analysis are calculated during the solving process. This is a complicated process whereby a set of coupled differential and algebraic equations, DAE, define the equations of motion of a SolidWorks motion model. A solution to these equations is obtained by integrating the differential equations in such a way that the algebraic constraint equations are also satisfied at each step. The speed of the solution depends upon the numerical stiffness of these equations. The stiffer the equations, the slower the solution. Special efficient integration methods are required to solve numerically differential equations, because the usual methods for solving differential equations perform poorly and are too slow. The SolidWorks Motion Solver offers three stiff integration methods for computing motion. Those are GSTIFF, WSTIFF, and Stabilized Index 2, SI2, integrators. Each of these integrators are best used in specific situations but may not work well if used to solve the wrong type of simulation. The GSTIFF integration method developed by C.W. Gear is a variable order and variable step size integration method. It is the default method used by the SolidWorks Motion Solver. It uses backward difference formulation. The GSTIFF method is a fast and accurate method for computing displacements for a wide range of motion analysis problems. The coefficients used internally by GSTIFF are calculated assuming a constant step size. GSTIFF introduces a small error in the solution. WSTIFF is another variable order and variable step size stiff integrator. Both methods are very similar in formulation and behavior. Both of them use a backward difference formulation. The only difference is that the coefficients used internally by GSTIFF are calculated assuming a constant step size, whereas in WSTIFF, these coefficients are a function of the step size. So, if the step size changes suddenly during integration, GSTIFF introduces a small error in the solution, whereas WSTIFF can handle it without any loss of accuracy. So the problems run more smoothly in WSTIFF. In this method, sudden step size changes occur whenever there are discontinuous forces, discontinuous motions, or abrupt events, such as 3D contacts in the model. The Stabilized Index 2, SI2 method offered in SolidWorks Motion is a modification of the GSTIFF integration method. This method provides better error control over velocity and acceleration terms in the equations of motion. Provided the motion is sufficiently smooth, SI2 velocity and acceleration results are more accurate than those computed with GSTIFF or WSTIFF, even for motions with high-frequency oscillations. SI2 is also more accurate with smaller step sizes. This method is significantly slower for smaller step size. Instability points can be defined as instances where self-equilibrated structure does not move. However, a small impulse in either direction will result in rapid motion during which the stored elastic energy is rapidly transformed into kinetic energy. Note that such instances are difficult to overcome numerically. Let's see how to set advanced motion analysis options. Click Show Me to launch a demonstration video. We will reduce the accuracy so that the solver will handle the over-center solution. Click Motion Study Properties. To save more instances of data on the disk in frames per second, enter 200. Click Use Precise Contact. Accuracy and the maximum integrator step size parameters have significant impact on the contact solution and should be used first when contact solution problems occur. To reduce the accuracy, enter 0.001. Scroll down and click Advanced Options. Click the Integrator Type drop-down arrow and then click WSTIFF. Remember, this solver is best used when the step size changes suddenly during integration. In this case, the step size changes very quickly when the latch comes into contact with the keeper. To reduce the maximum integrator step size, enter 0.0005. Click OK to close Advanced Motion Analysis options. Click OK to close Motion Study Properties. Click Calculate. This time, the simulation will run, but it may take several minutes to complete. Please wait while the simulation is in progress. Reduce the speed of animation to 25%. To play the animation again, click Play from Start. Notice that when the latch is closed, there is a small oscillation because all the energy is not being damped. This does not happen in the physical model, and it is a sign that the damping values used in this simulation can be increased to represent the real situation more closely. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about setting advanced motion analysis options. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Here is a question to check your understanding of what has been covered so far. Default plots are created with the x-axis showing the duration of the simulation and the y-axis scaled to the maximum value of the variable being plotted. There are times when we want to scale the plots differently. Using chart properties, almost all aspects of a plot can be modified, such as chart titles, background color, axis values, and many more properties. Let's see how to plot results. Click Show Me to launch a demonstration video. Now, we will plot the contact forces between the latch and the keeper. Click Results and Plots. Select Forces as the category. Under Subcategory, select Contact Force. For Result component, select Magnitude. Now, we need to select the faces of the keeper and latch. Click the face of the keeper. Click the face of the latch. Click OK. We can observe that the graph exhibits significant oscillations with apparently unbounded peaks. The time interval, approximately between 2.80 seconds and 3.5 seconds, corresponds to the small oscillations observed when the latch mechanism is closed. Each one of those peaks corresponds to an impact or collision force, magnitude of which depends nearly exclusively on the contact stiffness characteristics. Because these are highly approximate, the peaks of the impact forces in this interval should be ignored. We will now modify the chart, enabling us to see beyond the noise. Now, we will modify the plot's axis properties. To modify the x-axis properties of plot 1, right-click on the x-axis of the plot and click Axis Properties. Click Scale. Clear Endpoint. Enter 3 as the new endpoint value of the x-axis. Click OK to close the Format Axis dialog. To modify the y-axis properties of plot 1, right-click the y-axis of the plot. Enter 150 in the endpoint field. Click OK to close the Format Axis dialog. We have a very sharp peak at 0.5 seconds where the spring hits the carriage. Because the peak is so sharp, and the contact force at this instance qualifies as an impact or collision force, we do not know how accurate this data is. We would need accurate contact elasticity parameters and more data points to get better accuracy and understand this impact force. Just before 2.5 seconds, the latch reaches over the center point and we see the maximum contact force of about 36 newtons. This solution is reliable, and its dependence on the contact parameters is significantly smaller than at point 1. Move the cursor over the data points and the callout will show that the maximum value is 37 newtons at 2.53 seconds. Click Close to close plot 1. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about plotting results. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Let's see how to create a torque plot. Click Show Me to launch a demonstration video. Now we will create a plot of torque required to close the latch. Once we have a torque plot, we can easily determine how much force will be required to close the latch. Click Results and Plots. We need to follow the same procedure to define the plot using forces, motor torque, and magnitude. Select the rotary motor which closes the latch as the simulation element. Click OK to create the new plot. In Plot 2, again, we observe similar peaks after approximately 2.80 seconds. Each one of those peaks corresponds to an impact or collision force, magnitude of which depends nearly exclusively on the contact stiffness characteristics. Because these are highly approximate, the peaks of the impact forces in this interval should be ignored. Now, we will modify Plot 2 to show the first 3 seconds and a maximum magnitude of 200 Newton millimeters. Right-click X-axis and click Axis Properties. Clear Endpoint and enter 3 as the new endpoint value of the X-axis. Click OK to close the Format Axis dialog. To modify the Y-axis properties of Plot 2, right-click Y-axis and click Axis Properties. Clear Endpoint and enter 200 as the new endpoint value of the Y-axis. Close the Format Axis dialog. We can see a maximum torque of 97 Newton millimeters at about 2.09 seconds. To close Plot 2, click Close. Now that we know the torque required to rotate the latch, we can now determine the force required by dividing the torque by the distance over which the closing force acts, which we will measure now. Click Evaluate. Click Measure. Click the edge of the series lever. Click the axis of the series lever. We can see that the distance between the end of the latch and the axis on which the motor acts is 25.04 millimeters. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about creating a torque plot. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. After finding the torque required to rotate the latch and the distance between the end of the latch and the axis motor, we can determine the force required to close the latch using a formula. Force equals torque divided by distance. In the Show Me, creating a torque plot, we have seen that the maximum torque is 97 Newton millimeters and the distance between the end of the latch and the axis on which the motor acts is 25.04 millimeters. Using torque and distance, the required force is 3.87 newtons. Here's a question to check your understanding of what has been covered so far. You've reached the end of the module Understanding Advanced Contacts Part 2. Here are the key takeaways from the module. Click each tab to learn more. Here is a chance for you to practice what you have learned. Offline exercises are available for this module. To attempt these exercises, you must have access to a SolidWorks installation. To complete each exercise, download the self-extracting executable file from the e-course details page on mysolidworks.com. This file contains the sample models and exercise PDF file for every module in the e-course.